This lesson is for 9.5 functions and their inverses. The two big ideas are 1. Determine whether the inverse of a function is a function, and 2. Write rules for the inverses of functions. Looking down here, if any horizontal line passes through more than one point on the graph, the inverse is not a function. As you can see from the two examples, I could apply what's called the horizontal line test, HLT for short, that if at any time on the graph, like in the second example, if a horizontal line would intersect the graph at two or more points, then the inverse of that function would not be a function. What would this second example look like? Well, its inverse will be something to that effect, and as you can see, it will fail the vertical line test, intersecting the graph at two or more points. So in other words, if you want to know if the inverse of a given function will also be a function, apply the horizontal line test to the original function's graph. Looking at the first example, we could assume this is exponential, and any vertical line, horizontal line, that we lay over top of the graph intersects at most once with the graph. Therefore, if we take a look at its inverse, which would be logarithmic, and then apply the vertical line test to this function to determine if it is a function, it passes with flying colors. So the difference between the horizontal line test and the vertical line test. The horizontal line test is a predictor. It allows you to predict if the inverse of the function will be a function. The vertical line test allows you to assess with the function that's currently in front of you whether the graph represents a function. Looking at the two examples below with the directions of using the horizontal line test to determine whether the inverses of each relation is a function, we go ahead and use the horizontal line test. This parabola here that's vertically oriented fails the horizontal line test, so we will say no. Fails HLT, which means if I were to invert this function, and then it would look something like this. It would now be a horizontal parabola, and then at any time with the function immediately in front of you, if you want to know if it is a function, it must pass the vertical line test, and this sideways parabola does not. Looking at the next example, no matter where we place a horizontal line, it passes the horizontal line test. Therefore, the inverse of this function will be a function. And let me re-say that. This is currently a relation because it itself fails the vertical line test. So it is not a function, so it is only a relation. But the inverse of this function relation will be a function. And if I quickly sketch what the inverse will look like, it would be like a sinusoidal wave, and then applying the vertical line test to it, this function in front of us passes. Looking now at the algebraic side of inverse functions, we need to swap the x and y, solving for the y in its new position. In doing so, you invert the domain and range. The notation, you use a superscripted -1 on the original function. That -1 does not mean that you reciprocate and rewrite as 1 on f of x Rather, what the superscripted notation is the general symbol that we will use for the inverse of a function. As we mentioned, visually there are two ways to determine if the inverse is a function. You could apply the HLT to the graph of the original, or you could apply the VLT to the graph of the inverse. Now the domain and range of the inverse is the range and domain of the original function. So they switch. Specifically, a one-to-one function is a special type of function, a subset of functions, that occurs only when its inverse is also a function. The reason this is called one-to-one is because every input of the domain is matched to one output of the range for the original function, and the same holds true for the inverse function, hence the name one-to-one. So if we take a student by the name of Kimberly Smith, her name is a one-to-one function because Kimberly, the domain, is mapped to one last name, Smith, and vice versa. If you invert and list her name alphabetically by her last name, then you would say Smith Kimberly. And that's assuming if there were no other students by the name of Kimberly or Smith in the classroom. Moving to our first example, find the inverse of the function. So we'll swap x and y and solve for the y in its new position, and then use this inverse notation for the function to mark what we found in relation to the original, and then determine whether it is a function and state its domain and range. So for part A, note that f of x is another way of writing the y, so we will swap the input with the output, the domain and the range. So that's what it means to find the inverse. But now we want to define this with respect to the domain, so then we need to isolate the y, cubing both sides. And now that we got y by itself, we need to mark that as the inverse. So we use the inverse of f of x is equal to x cubed minus 1 for part A. In this example, there are two ways in part B to determine whether what we found is in fact a function. You could consider the graph of the original, which would look as a cube root function, something to this effect. And note that it passes HLT which means that the inverse of f of x must be a function. So that would be one way to decide if what you found down here is in fact a function. The other way to decide if what you find is a function is to graph it, and here as a cube, then you can graph it and then apply the vertical line test. It passes VLT, and so these are two ways that you could determine whether it is a function. You could use one or the other. Sometimes the original function, you're familiar with it and whether it is a function and whether it passes HLT, so you'll use that. Other times, it may be easier to look at the resulting function that you inverted and then apply VLT. For part C, stating the domain and range, if you're familiar with the first function, in this case we have a cube root function, which looks like this graph, and so then the domain is a set of reals, and the range of the original is a set of reals. Then define the domain and range of the inverse. You could just swap the domain and range of the original function. Since it's all the set of reals, it's not too difficult here. You could use that approach if you are solid on what the original function's domain and range is, and then you just swap it to find the domain and range of the inverse function. However, if you are more comfortable with recognizing what the domain and range is of the inverse function, then you could just find it directly. In the next example, we'll see a little more interesting result regarding whether what we get is an inverse and how to talk about the domain and range, because it won't just be the set of reals this time. We're starting off with a quadratic. So for part A, we swap the input with the output, the x and the y, where f of x is equal to y. Proceed to solve for y in its new position. So take the square root of both sides, positive and negative case. At that moment, we now create two range values or y values for every x value or domain value that we input into this function. So right now you could understand that the inverse will not be a function. We'll consider that further in a moment. Continuing to isolate the y, add 1 and divide by 3. And for full credit, we mark that we found the inverse of the function. And if that was like say g of x, then this would be the inverse of g of x. So notice what we just found is pretty hard to understand. And I put a 3 in there by accident. So that's the square root of x. So we have a very interesting square root function, both with a positive and negative case. So we started off our graph with something that looked like this, and now we're ending up with something that looks like this. But how to graph it based on this function, you could make it 1/3 positive or negative 1/3 square root of x, so then you have a vertical compression by 1/3 and a VT 1/3. But I think it's a lot easier just to study the quadratic to answer the remaining questions for this problem. Moving on to part B. Determining whether it is a function. I will apply the horizontal line test to the original graph. Because f of x is quadratic, it passes HLT. You know, the graph will look something like this. And I said passes, I meant to say fail. That fails HLT. So the answer is no. And the reason? That f of x fails HLT. Now for practice, even though, or not even just for practice, even if the inverse is not a function, it still has a domain and range. So looking at this inverse function, it's going to be pretty hard to decide what the domain and range is. It's a lot easier to check out the parent graph, not the parent, but the original function in the problem. So if we analyze it, we're going to see that it has some horizontal transformations, so we could rewrite this. Oh, if they're only horizontal transformations, and the domain for a vertical-oriented quadratic is always the set of reals, then the domain for the inverse will also be, well, let me not get ahead of myself here. So the domain of f of x is the set of reals because it's quadratic and it's vertically opening. And then the range is y greater than or equal to 0. And there were no vertical translations or reflections over the x-axis, so that will not change. Therefore, we could swap the domain and range for the inverse function's domain and range. I'll leave out writing what's going on down here as a subscript, and I'll just say that domain is now x greater than or equal to 0. Domain is the input dependent variable x, and then the range is now the set of reals, so they swap. So keeping that in mind, because we literally swap the input with the output at the very beginning, that makes finding the domain and range easier sometimes in the end. The last section is showing functions are inverses using composition. So we are going to find f composed with g with respect to x, and if that equals x, and you have to do both directions with the composition that g composed with f with respect to x is also equal to x. If those two things are true, then yes, g and f are inverses. And understand what it means to compose one function in with another, that and get x out. It means that the two functions undo one another, because g has a rule that takes the inputs and generates an output. F does the same thing in its own way. But what happens is if you take their compositions and you get x, that means you put something in, let's say a 5, and it spit back out a 5. You put in a 3, and it gave you back a 3. So the f and the g are undoing themselves, each other, meaning that they are inverses. And it has to be true for both directions of the composition. And that's really just for special cases, specifically when you have restricted domains like for square roots and quadratics. So be on the safe side and always check both. That's required for full credit. Notice the directions. Determine by composition whether each pair of functions are inverses. So we will take a look at f composed with respect to g of x. It doesn't matter which composition you do first. If at any time either of the compositions do not equal x, then you could stop and say that the two functions are not inverses. So let's substitute in g of x's rule into f of x. So that means this is going to go right there. Could just get right to the point. That's what it means to compose functions, substituting the one rule into the other in place of the independent variable. Now we'll distribute that 3. Don't just multiply that 3 by the 1/3 and forget about the plus 1. Now a third of 3 is 1x, but then 3 times the 1 makes a 3 there, and minus 1. Now that's not too difficult to see that equals x plus 2, but it doesn't matter what it equals. As long as it's different than x, then our answer is no, f and g are not inverse pairs. And you could just simply write no, and the fact that you showed that one of the compositions, at least one, did not produce x, then you've completed the full problem. For the next example, we'll start off again, posing f with respect to g. So we'll take g of x's rule and substitute it in for the x in f of x. So this will substitute in right in there. Combining like terms, dividing by a fraction, multiplied by the reciprocal, and voila. We ended up with one of the compositions equaling x, so now we must check the other composition, g with respect to f of x. So now I'm going to take f of x's rule and use it as the independent variable in g of x. So I'm going to take all of this and substitute it right there, wherever you see an x. Dividing by a fraction, multiplied by the reciprocal, and you can see we get x again in both cases. So yes, f and g are inverse pairs.